Welcome. And today we are going to discuss about transformers. So transformer models are a class of neural network models that use the transformer architecture, and they have become really popular in natural language processing and have achieved state-of-the-art performance on the range of NLP tasks like language translation, text classification, and so on. So let's just look at the transformer architecture here. The original transformer architecture is based on encoder-decoder architecture that is widely used in tasks like machine translation, where a sequence of words is translated from one language to another. So this architecture contains two parts, and one is an encoder and the other one is a decoder. What we see in the upper half is the encoder part, and what you see in the lower half is the decoder part. An encoder is essentially something that converts the input sequence of tokens into sequence of embedding vectors, often called as hidden state or context. A decoder uses the encoder's hidden state to iteratively generate an output sequence of tokens, one token at a time. Let's look at the picture now. So for a typical NLP project, what we'll have is sentence as input. So we'll need to convert that sentences into tokens. And once we input those tokens into the transformer has token encodings. So token encodings are going to convert them into different embeddings. Here different embedding layers are necessary for encoding different informations about the inputting sentence. For example, the tokens are encoded to embeddings, and then also the positional embeddings is taken into consideration because it's really essential to understand the syntactical understanding of the sentence as well. So the position of every word with respect to each other is really necessary to encode it into an embedding, and those embeddings will be passed into an encoder stack, which is going to have the attention layers in it. So once we have that kind of a setup, and after our embedding layers are outputted from the encoder stack, a hidden state is produced from the encoder model. And this encoder, the output of the encoding or hidden state as it calls it in here. So this hidden state has to be given into the decoder stack. And depending on our task, the decoder is going to, we can design it in certain ways that it would be really helpful for our particular problem that we are going to deal with. So if you're looking at a classification problem like sentence classification, sentence similarity classification maybe, or sentiment analysis, or any kind of language based classification or probability based of a model, what we are going to use is a classification head, just like we have done on the BERT project. So sentiment analysis with BERT. So what we have done in that is we had a pre-trained transformer. So a pre-trained transformer is nothing but, let's just take the case of BERT, and BERT is just an encoder only model. So essentially there are three different kinds of model: encoder model, decoder model, or encoder decoder model. So encoder model is only going to have this encoder part in it, which is only for encoding some sentence into meaningful real number representations. So those meaningful representations can be taken and then can be made part of a classification pipeline and can be used to produce different probabilities for classification. So in this setup also, maybe our let's just say our transformer is already pre-trained, and it's pre-trained on some specific sort of language data. Let's just say a domain specific of different social, or let's just say it in the field of sports or sports question answering domain. So in that case, the weight representation or the language representation finally that we have in here is going to be a domain specific. So if you are going to use that for a different domain, then that would not be the best you can do. But the best you can do once you get any pre-trained transformer is to fine tune it. So that's what we have done in BERT project as well. So we took the bird and we sort of formed this sort of a model that ranging from the input that we take, and it will produce the encoding, and once it produced the encode, we would take the encoding and we would create a decoder and attach a classification head into it, and we will make a classification pipeline as such. So problems could be even different also. So in this case, a classification problem, what we wanted to output was just probabilities, real numbers, and then we would do the back propagation and fine tune it. That's one way of doing it. But the other way, there could be different problems arising when you want to do sequence to sequence models, such as text to text, like machine translation, or text to audio, or text to image, or any that kind of sequence to sequence models. Then you'll need to produce a sequence after the decoder. For a sequence to sequence model, what we'll do is the encoder output is fed to each decoder layer, and the decoder then generates a prediction for the most probable next token in the sentence. Then this output of this step is then fed back into the decoder to generate the next token, and so on until a special end of sequence token is reached. So that's the format of making a sequence to sequence model. Let's now look at the encoder and the encoder stack. So inside of the encoder stack, what we have is something called multi-head self-attention and feed-forward layers. So what it does is it really captures the semantic understanding of the sentence, and the self-attention mechanism is what makes that possible. And this is what essentially captures the meaning of the sentence and different relationship between the different words in the sentence. And that is what the best representation of our sentence is, which is what we get as an output in the hidden states here. Decoder as well, what we are going to see is attention layers. So these attention layers is what makes it possible to convert a language representation in real numbers to another language representation and decode that into tokens in a different language. So now we'll talk about attention a little bit. Attention is a mechanism that allows neural network to assign different amount of weights or attention to each element in a sequence. For text sequences, the elements are token embeddings, as we have seen in here. So I said the tokens will be converted to embeddings, where each token is mapped to a vector of some fixed dimension. For example, in BERT, each token is represented as a 768 dimension vector, and the output as well is like a 768 dimensional vector in case of BERT. So the self part of the self-attention refers to the fact that these weights are computed for all hidden states in the same set. The main idea behind self-attention is that instead of using a fixed embedding for each token, we can use a whole sequence to compute a weighted average of each embedding. So that's what essentially we are performing when it comes to self-attention. There are several ways to implement a self-attention layer, but the most common one is called scaled dot product attention. So you can just keep that in mind and refer around it so that you will have a good understanding of different kind of attention layers and everything. So as I've discussed earlier, we have three different sort of architectures when it comes to transformers. So encoder only transformers, decoder only transformers, or encoder decoder transformers. So you can look at some of the examples of all of them. So these are encoder only transformers, BERT, which we have dealt with earlier, and decoder transformers are here listed, and encoder decoder transformers in the center. So these are just examples of different transformer models. With that, we will go to a project which is going to be named entity recognition. We'll use a transformer pre-trained transformer model. So let's start. Today in this video, we are going to look at how we can do named entity recognition on medical data. So I have loaded the medical data. These are medical tweet data, so I have loaded that in. So let's start. So we need to import a couple of things here. Import Spacey, import pandas, tqdm.utter import trange. So Spacey is a powerful modern natural language processing library that is designed for developers to build and scale efficient language processing pipelines. And it provides easy to use interface for processing text data, and it has features including part of speech tagging, named entity recognition, dependency parsing, and so on and so forth. So also Spacey has different transformer models, and one of them is, and we are going to load one of them for our named entity recognition task now. So I'll show you how to download one of its model and load it and successfully use it for NER. Okay, so let's download one of the models. So Python Spacey download Ian core small. So this is the model that we are going to use, a transformer model. The name suggests, this SM suggests it's a smaller model, so we got a larger model as well, and it's trained on the web data, and it's English. And we need to import the data. So pd.read, it's a JSON format file, JSON of, I have already loaded the data, so, and I need to transpose it. The reason why I'm transposing is it because I already looked at the data, and the data needs to be transposed. We have already imported Spacey, and the model also has been downloaded from Spacey. So we need to load the model, and the thing that we need to do is make an NLP object. NLP equals to Spacey dot load Ian core web small, and this is going to be our NLP object. So before we dive into this, I need to explain why do we need to do NER, because in some cases, in this, for example, in this case also, we have a lot of tweets and the text for a lot of tweets, and this is coming from a medical hashtag of some sort, and there could be different things like hospital names or names of people, and hashtagged different hospital names or places, or maybe different diseases, things like that. So these are the things the tweets are actually around, and these topics. So we need to extract different topics each of the tweets is talking about, and there could be different entities. So naming like name of a person, organization name, or name of a city, or a name of or even percentage, or different things like that. So as we do this thing, you'll have a good understanding of that. So if you want to extract all of that entities from every sentence, then you have to use one of these models and use Spacey to extract it. So that's what exactly we are going to do now. So we'll first look at how we can do it in one simple text, and we'll repeat that for the entire data frame and save it into, or sort of like extend the data frame to contain all of the entities as well. What we need to do is, we have Spacey imported, and NLP is equal to Spacey. We have loaded the model as well. So next we need to define a text that we want to analyze. So for data dot I think tweet text was the column that we had our tweets in, and let's just say I'm taking the 0th row, or let's just take any sort of row, and the text you can see. So this is the text we have, which is a small text. Let's just take a bigger text. We'll take this thing, and what we need to do is NLP text equals to, we also selected the text. Now we need to make a doc object which has to be NLP of text that we created, and this doc, and through this doc entity for entity in doc.enthusiast, we can print entity dot label comma entity dot text. So these are the entities that we have in here. So some of them can be wrongly determined as well. So it all depends on how good is the model is. So here it's some name, some person's name as rightly recognized as a person entity, an organization, a geopolitical location, and there are different things like time and date and product. A lot of the things are actually labeled correctly. So this is what we are going to do now. So this is just for one of the tweets, and we are extracting all of the entities from one of the tweets. So now we will try to extract entities from all of the every tweet and save it into its respective columns. One more thing that we can actually try to do is, so as an extension, one more thing that you can do is, once you find the entities from each of the tweets, then you can also figure out maybe the sentiment associated with the tweet using a sentiment model. That's a separate task. And once you figure out both of the things, a tweet has some sentiment, also has some of the entities that we have recognized. So there is a higher chance that these entities could be directly correlated to the sentiment of the sentence. So once you have a lot of the tweets, and you can extract, or you can maybe take like a sentiment score for each of the entities recognized from every tweet, and the average sentiment associated with and then you can average the sentiment, and that would be the sentiment associated with the entity. So if you are looking for any key entities and the sentiment associated with it in a corpus, that would be a valuable information to understand. So let's just do it. We will not be doing the sentiment part. I will leave it to you to extend it, but we are going to do a entity recognition completely in the corpus provided. So for that, we need to write a small chunk of code. So I have defined the NLP here already, and I need to iterate through for index in the range of len of data, and txt equals to data of tweet text of index. And I'll need to create a doc object here for specifically for this text, and NLP equals to txt doc equals to NLP of txt, and then we'll iterate for entity in doc dot enthusiast if what we have to make is different columns. So the idea is to what our data looks like is something like this. So we have tweets and others. So let's just say we have found two entities in here. One is organization, and the other one is a geopolitical entity, and I want it to be in the column here. So I want to make like a column of an organization and a geopolitical entity or column, and I want to have in the column here, I need to have the value of the text of the entity in each of the column. So we are going to repeat that process for the entire data. So if entity ent dot label not in let's define something called labels here. Labels equals to an empty list. So if the entity is not in labels, we'll need to create the label. And I want to store, so there could be multiple organization in each tweet, and there could be multiple places the same organization name is coming in each tweet. So I don't want to extract that multiple times. I don't want to have duplicates in my data, so I need to account for that as well. So I need to essentially put this into a list. You can also do set, but since you are iterating it, list is going to be much better in this case, because you are going like one at a time. So we got our data and data of so I need to create a label data dot a column ent dot label, and that would be pd dot series of, and I will create empty lists in this one for I in range len of data. And this means like all of the columns will be initialized with empty list, and data of ent dot label of index, and I'll append ent dot text, and also append labels dot append ent dot label. And this is for the case when I don't have an entity as a column. This is for a fresh entity to come in, and if I already have the entity, then I only have to check if the entity already exists in the column, and if it doesn't, I need to append it to the column. So if ent dot text not in data ent dot label index, this is the case, data of ent dot label of index dot append ent dot text. So once you run that, our problem is solved. So you're gonna also, one more thing that we'll need to take care is, previously the indexes were not 1 2 3 4, so we expected the indexes to be 1 2 3 4. So I need to dot drop index reset index drop equals to true. So, and it's running. Now that it's run, we can check out our data. Yeah, so data looks like this now. So different columns being added, and all of the columns are actually the entity labels, and these are the text associated with the entity. So different organizations in each of the tweet, and different things like that. So it looks perfect. So this is it. You can go ahead and make that sentiment analysis part also, which I have explained in the video, and try to implement that